I'm not a doctor. I work in an engineering group, so this will be a very much a technological perspective on things. And the work I've been doing over the years has been very ICU related. So when Jan asked me to speak, he said, could we try and give a flavor of the progression of clinical decision support related to mechanical ventilation from the ICU to the operating room. So I hope that it'll be a talk that will inspire many questions and comments, and will also illustrate perhaps a little bit from my lack of knowledge in relation to the operating room, and give us some nice discussions because of that. So what have we learned? Well, if we've learned anything from Professor Hedenstjern's work, is that we need to set the ventilator based on physiological understanding. I think that's clear, and we need to consider all of the ventilator settings and the physiological understanding related with each of them. So if we're considering inspired oxygen, we do, of course, as has been well shown, need to consider the high levels of inspired oxygen are dangerous, and dangerous short term because of the absorption atelectasis, and back to the ICU again, dangerous in the long term because of the toxic nature of oxygen. So we have a number of factors which will push us to try and reduce inspired oxygen. And then we have a number of factors which push us to increase inspired oxygen, and that is, of course, hypoxemia. Be it local hypoxemia arterially or systemic, if we could access it in the venous compartments. And to answer the question how much oxygen I would like, which was posed, I would like one to measure my oxygen consumption, to measure my hemoglobin level, to calculate the inspired oxygen level that was necessary to fully saturate my hemoglobin to deliver sufficient to accommodate my oxygen consumption. That was what I would like. And if one can't do that calculation in head, I'd like you to get a computer that can do it. So that's what I would like. And that's where I think we should be moving, incorporating our physiological understanding to bedside practice, using our well-known mathematical knowledge of how things behave. And we've known many of these systems in quite some detail for quite some time. So this is the one compromise, but we have other compromises. We know from the ICU again, in the ICU, that low tidal volumes are protective, low driving pressures are protective, accommodated by the correct PEEP level, of course. And that's being started to move across. My expertise in this is much less than Professor Hedenstjern, but there's been a couple of recent guideline papers. This one from Foutier, suggesting in the healthy lung, this is the sick lung, of course, so this is the relationship between moving over from the ICU again, of keeping tidal volume 6 to 8, PEEP 6 to 8, low oxygen, inspired oxygen levels, interestingly enough, in this guideline. But just to illustrate perhaps some lack of agreement, there's agreement on the tidal volume here in the FiO2, but this is suggesting that in healthy lungs, PEEP should be less than 2. And this was a review article, again, with the authors primarily coming from the Pravillo study, suggesting that the lower PEEP levels. So there is some controversy. But I think we'd all agree. I mean, if we're in an ICU, right, and you have a plateau pressure of 30 and a pH of 7.4, the compromise is badly set, right? If you have a plateau pressure of 20 and a pH of 7.4, maybe that's okay, right? And maybe if it's 30, you want to be considering lower pH levels to make permissive hypercapnia. So there's a balance, and that balance, like oxygen, is related to physiology. If you have stiff lungs, you're protective on the pressures and volumes. If you have non-stiff lungs and very high CO2 production, then maybe you're willing to accommodate higher pressures and volumes. And this is why we see the trend to saying that tidal volume doesn't matter so much in healthy lungs, is because, well, the compromise point is at a different position. We're trying to get rid of our CO2 effectively. But we have a balance. And thirdly, of course, is once patients start breathing spontaneously, we have a balance on how we wish to support them. If we over-pressurize them, this is pressure support again, and I relate back to the ICU. If we over-support them, we will damp their respiratory drive. We will prevent them from coming and triggering the ventilator and exercising their diaphragm. If we under-support them, we'll make them stressed, their metabolism will go up, they'll get rapid shallow breathing. So we want to make the balances appropriately. And there are all sorts of other risk factors, of course, illustrated here nicely in the critical care setting. And this might be an issue we want to consider as the patients are waking up in the operating room or in less invasive surgery where there is spontaneous ventilation. So, for me, mechanical ventilation is a question of balances. It's a question of setting ventilator settings to accommodate balances related to the individual patient's physiological characteristic. And one can make a visualization of this by drawing a hexagon and placing the balances on opposing corners of the hexagon. And then one can separate out the settings and the hexagon, and then the question becomes, how do we optimize the settings according to the individual patient's response to achieve the correct balance of ventilator settings? That, to my mind, is a rational decision-making process. So, if you agree with that process, then the question is, how do we represent, in a technological sense, a patient's response? And there are many different ways, or several at least. There are clinical rules, so one can implement systems which have the characterization of if CO2 high and lung mechanics not a problem, then increase tidal volume. Sort of clinical heuristic rules of thumb. Okay? One can implement neural networks or other black box model techniques which correlate statistically inputs and outputs, learn standard patterns and implement those. Or one can go back to physiology, and I'm sure by now you can guess what I prefer, but these are the tools we have at our disposal. And I forgot to actually mention I have a conflict of interest. I should have said it at the start. I'm a board member and a minor shareholder in a company which produces some of the technology I'm going to talk a little about, which of course colors my tendency to favor the physiological aspect, and so I should acknowledge that. But I would like to pay due credit to what we have already, in great extent, some systems that have been really at the forefront of trying to provide clinical decision support for mechanical ventilation. And they're primarily, again, in intensive care, but there are some developments moving them elsewhere. If I start by just looking a little at the system that used to be called Ganesh and now is Draeger's smart care system. And this is a system based on these types of production rules. It's a system for ventilator weaning in the ICU, and it's a closed-loop system, so there's no necessity for interaction with the clinician, and it regulates the pressure support trying to wean the patient. And what it does is tries to keep the patient within a zone of comfort, as it's called, to prevent them from having rapid shallow breathing and for normalize their end-tidal CO2. That's essentially the functionality. It has quite a rich history in the literature, starting with the studies of Doja and Bouchard in the early 90s, which were small studies showing that if you implemented the system in intensive care, then you could keep the patient within the predefined levels of the zone of comfort. So it stabilized the physiology as defined by the system itself. And then more recent studies looking at larger scale, now that it's the smart care system, which have shown in some of the studies reduced length of stay and weaning times. So there's been a recent Cochrane report on this, agreeing with that, albeit based on relatively smaller data sets, I believe was the absolute conclusion. So great breakthrough there. My emphasis is here is to talk about the technology. What they have, I have noticed recently, is that they've now brought this a system for that out into the operating room, which they call Smart Ventilation Control. I personally haven't seen any studies related to that as yet. You might know more than me. Then again in the ICU, Philips have come with a Ventasys system, which uses neural networks and some rules with something called fuzzy logic on top, which I won't go into. It's an open loop system, so now it intends to interact with the clinician and provide advice. And the artificial neural networks, these black box statistical models, they are trying to remove the need for esophageal catheters. So what they're doing is they've done several studies related to trying to say, can we predict the transpulmonary pressure, the patient's work of breathing, without the need for esophageal measurements? And then they've packaged these into black box models and included them into the system. And of course, if we don't need esophageal measurements for patients, then that's a very productive thing. And there's a huge amount of literature at the moment looking at the use of esophageal measurements in the intensive care. The literature is a little less mature in this sense. There's been studies looking at the use of neural networks related to power of breathing. And then there has been a couple of studies saying that if you use that system in the ICU, you provide similar ventilator settings to those that would be provided by the clinician in a kind of a crossover way. Probably the most mature of the systems that are available, again, not in the OR, but generally in the ICU, is adaptive support ventilation, or now IntelliVent, which is again based on rules, but now with some underlying physiological models, the Otis model, describing patients' work of breathing for patients who have spontaneous breathing activity. Again, a closed-loop system directly controlling the ventilator. And the literature here is more mature. There's been studies, earlier studies, looking at the ability of the safety of the system to keep it within ranges. And more later studies here now looking at controlling within general ICU. Perhaps of most interest to this audience is that they've done a number of studies related to post-operative extubation times, and shown shorter length of times in fast-track cardiac patients to extubation. Now, one may argue, is reductions of those times a huge clinical problem, but it has been argued that any reduction in time and any need to get the patient away from the post-operative situation more quickly can be beneficial. So that's a very, very brief state of the art, and it would be shy of me to say that there isn't masses of other things, and the work in Utah of Alan Morris on their clinical rule-based system for ventilation control has dominated the literature for many years, and there are many breath-by-breath control systems that the manufacturers are coming out with NAVA and PAV that also have great importance, but I'm not covering those now. Okay, so that's this kind of the state of the art in what one can do. And I would like now to return a little bit to this physiological track on how we may have potential for incorporating more physiology. So if we're going to look at patient response, can we do it in physiological terms? Can we represent the gas exchange, the mechanics, the respiratory drive, ventilation, metabolism, and acid-base status in such a way that it provides us with a tool to monitor the patient during the operative period based on these and set the ventilator appropriately? So it would be nice to have these in the operating theatre. Why? Well, because there's a large interaction between them and we could learn about them individually and their interaction. Also because then we could begin to account for the effects of pre-existing disease. And additionally, maybe then we could monitor the change in patient stent during the operative procedure. And that's not the end of the story. As has been pointed out, we want to know what's happening to them post-operatively. We want to know whether the atelectasis persists. And if we could measure pulmonary gas exchange during the surgery and post-operatively, maybe we would get continuity of monitoring. Similar with respiratory drive, we may want to look at it during the phase of waking up from surgery, but then we're also interested post-operatively, particularly now with the evidence for opioid-induced respiratory drive depression. So, if we have physiological representation, maybe we can get some continuity of care over the whole procedure. There's been, post-operatively, of course, we look at these effects with capnography and acoustic methods, and there's some of the companies that are now trying to make integrated indices to look at the post-operative period and identify events. I think it's all very good work, but maybe we can get a step deeper and look at the physiological progression of the patient. And maybe look toward getting some continuity of monitoring by deep physiological understanding. Okay, so that's my vision. So what have we been doing to try and get that? Well, we've been trying to build models of these systems and link them together with this purpose of controlling mechanical ventilation and at the same time understanding the individual patient's physiology. We've been looking at the metabolism and the gas exchange, at acid-base, at all of these systems, and building mathematical models. And the art here is not to build complicated mathematical models. The art is to take the complicated mathematical models of others and pare them down to something that can be useful at the bedside, where the measurements available are much less. So we started with pulmonary gas exchange some time ago, built a little 3-compartmental model where we allowed both the low VQ and high VQ to vary and had pulmonary shunt. And we characterized with simple changes in inspired oxygen the relationship of low VQ, high VQ, and shunt in preoperative patients, postoperative CABG, and ARDS patients here, where, of course, pulmonary shunt flattens the curve and low VQ pushes it across, so one can understand different components of the physiology by making simple changes in inspired oxygen. We understood that in different clinical scenarios, and were fortunate as well to visit Professor Herdenstjerne's laboratory and compare it with the nurse gas elimination techniques in animal damage models. At the same time, we built models of acid-base, and again, relying heavily on the work of such people as Ole Sigurd Andersen, and also on the other side of the debate, Peter Stewart, trying to build biochemical models which describe how blood reacts. And we tested those models in numerous situations against old literature data of acid addition to blood samples in vitro, of the way in which bicarbonate distributes over the interstitial fluid, and also in blood mixing experiments of our own to see if we could simulate the effects of shunted blood mixing with blood coming from other areas of the lung. And then we turned our attention to respiratory control, and we relied heavily on the work of John Duffin down here, who has built nice models of the CSF, the cerebral spinal fluid buffering. So what that means is if you have a COPD patient who has a naturally depressed drive because of the buffering characteristics of their CSF, you can automatically regulate that buffering, or you can have a model that automatically regulates that buffering and down-regulates the drive for COPD. So again, you have a reduced drive in a patient waking up if they have pre-existing COPD. We evaluated those models in the ICU by performing experiments of varying either volume support or pressure support at 5 different levels and seeing if we could predict changes in frequency, pH, and end-tidal CO2 in patients with spontaneous breathing activity. And we could predict those quite nicely. So we had these systems and we had links between these systems, but there was one missing, of course, and that is the effect of PEEP. And of course, the PEEP should change the gas exchange and lung mechanics. And we built something very crude and rudimentary there. What we built was a model which said that if you increase PEEP, you're likely to decrease shunt. If you have more shunt, you're likely to decrease it more. And if you have less shunt, you're likely to decrease it less. And similarly with compliance, and that you're likely to increase your high VQ, shifting your whole distribution over. If you build such a model and build it into a system, as the patient responds to PEEP, then you can change the model to learn from the patient's response. So if they are a non-responder, you tune the model to non-response as they non-respond. And then the compromise becomes one of applying the correct PEEP to achieve the appropriate oxygenation without too high pressures, dependent on the patient's response or not. And the compromises happen naturally. We were very fortunate a few years ago that there came a spin-off company from the university, and this is the one where I have the conflict of interest, who decided to try and build this and put it bedside in the ICU. So they have a little tablet now connected to the ventilator, as well as that indirect calorimetry device, so we can measure the VO2. So now we can do that trick of setting the FiO2 dependent on patient need. And that sits behind the ventilator screen, and it provides advice. So what happens in the machine is, as it's collecting the calorimetry and flow data and pressure data, it's fitting these models, and then it's searching the decision space for what is the best settings for the ventilator for this patient, given this patient's physiology. And then it suggests a step in that direction, and if the patient responds positively, the models are confirmed, and if they respond negatively, the models are retuned, and there becomes a learning process, and we head off in another direction. So if it's a patient on pressure support, and they're on a pressure support of 15, and it says, turn the pressure support down to 13, and the patient's metabolism shoots up and they get rapid shallow breathing, the system will recognize this automatically and push them up again. And you get this learning procedure and gradual adaptation in response to the patient. So now we have the models, now we have the measurement. You type in the blood gas, you have the indirect calorimetry and SpO2, so the system functions in that way. And I like to show you a couple of patient cases, and I hope I don't overstep the mark and it feels like a sales talk, but we've been working on this so long, so I'd like to show you how it functions, and then reflect it back to the OR. So this was a patient, 3 patients from the same day in an ICU in Italy. A very sick patient. Here's their hexagon, red around the edge. Here was the current setting, 78 of oxygen, pressure support of 10 and PEEP of 13. So the oxygen is saying a very high risk of toxicity, and should probably also be written absorption atelectasis there, but if we take that for given, then there is a danger with that high oxygen level. At the same time, they had a danger associated with low oxygenation. Yeah. And then the rest of the kind of penalties, as we call them, were moderate. So what does the system suggest? Well, first it learns the patient has a high shunt, and then it suggests to turn PEEP up a little and oxygen down a little, believing that the PEEP will potentially improve the gas exchange and mechanics, and therefore allow us to accommodate for the dangerous high oxygen level by pushing it down. I don't have a follow-up for this, right? I'd like you to just show you some kind of general cases. So that's one patient type. The next patient was a control ventilated patient, 35% oxygen, pressure control of 10, respiratory rate of 15 and a PEEP of 8. And their only problem was a little bit of acidosis. Right? So the system suggests push the frequency up a little and believes that that will cure the acidosis. And at the same time, because the patient looks so good, it says you can try and reduce the PEEP a little because, you know, the penalties look good, the patient looks better, so it's time to start pushing them off. And then the third case from the same day was a post-op thorax patient on support mode now, with 30% oxygen, pressure support of 7 and PEEP of 10. And you can see down in the bottom right-hand corner here that it says advice with a green tick, because it believed that the ventilator is set correctly. The PEEP to maybe compensate for a little post-operative atelectasis, and all other values to accommodate for the patient's needs. So that's where we stand. We've performed a couple of prospective studies with the system now. Studies in line with the studies of others, but we're not as mature in the development as others in the testing. These studies looking at, can we support the physiological progression of the patient over relatively short periods of time, 6 to 8 hours. Again, in the ICU, I will reflect back to the OR in a minute, I'm sorry. In the first one, we looked at the system without advice on PEEP, and we showed that in 25 patients, over a period of 6 hours, we could improve the status of the patient if the advice was taken, reducing tidal volumes by 1.1 milliliter per kilo in a significant way, reducing plateau and driving pressure, and oxygenation was as clinical practice, with about 40% inspired oxygen. Of course, I should tell you the details of this, but that's not time today. We did a similar study in Italy, again, relatively small numbers, but this time with the system with PEEP.
in Italy, it appeared they over-oxygenated the patients, and we could reduce inspired oxygen on average with 10% without significantly inducing an oxygenation problem. And at the same time, we also had moderate, non-significant, in this case, reductions in tidal volumes and plateau pressures, and increases in frequencies up to around 19, 20 on average. So we're getting some evidence that suggests that these techniques can be used at the bedside and provide an improved physiological condition. We're currently writing these studies up. They've only been published in abstract form right now. So the question then is, can these results be reproduced in the OR? And if they could, would it be associated with improved outcome? We're back to the question of, if you manage the patient well in the OR in terms of their lungs, does it make any difference, or is it just 3 clicks on the opioids thereafter that generates all the apneas? So we don't know is the answer. We don't have a proven system in the OR, but here comes my speculation again. Perhaps if we began to monitor on a deeper physiological progression and had some continuity of monitoring between the phases, then we'd be able to study these things more easily. Back to this picture of, if we could measure these things routinely and transfer them to the postoperative phase. And if, on our system, if you click a particular button, here's the hexagon behind, you get the physiological description of the patient. A patient here with shunt of 38 and a low compliance. We're currently working on the end expiratory lung volume. These are the parameters related to the drive, if we have them. They are the strong iron difference in the CSF and a threshold. I won't go through that. And we have the blood characteristics and the metabolic measurements from the indirect calorimetry and the estimated cardiac output. So we have the description of the patient. And if we could follow that description of the patient, we can start thinking about deep physiological monitoring. We can start thinking about intelligent alarms, alarms that pop up and say shunt has increased by 10%, rather than the pulse ox has fallen off. We've done a little of this ourselves. Some time ago, we did some post-op studies looking at the shunt and low VQ using simple inspiratory oxygen variation, looking at the progression from pre-op, 48 hours, 128 hours later, showing as much of the literature does that it's initial shunt, and then 2 or 3 days later you get a worsening of pulmonary gas exchange, which in my mind, in conjunction with a reduction in respiratory drive, potentially should be quite dangerous. And this respiratory drive opioid effect is something that I'm very interested in right at this moment. And I'd just like to finish by showing you a data set that I collected last week using the system of a patient in the ICU again, and I do apologize again, where this patient was given an opioid bolus here around 90 minutes, and their frequency fell from about mid-30s to 13. The tidal volume increased. Their minute ventilation fell, as did their alveolar ventilation. The system does a continuous serial dead space estimate, so we can plot the alveolar ventilation. And their metabolism also almost halved. Oh, no. 350 to 220 here. You can see it's almost a step function. And not only did it do it for the CO2, it also did it for the oxygen. You can't see that here, but you can see the respiratory quotient was constant. So the oxygen signal said the same. And this data, and I wish I had the results to show you, but this data is sufficient to estimate parameters describing respiratory drive. So this is sufficient. These step changes are sufficient to monitor progression of respiratory drive as the patient is waking up. And if we could transfer those into the post-operative setting, maybe we have some continuity of care there in monitoring respiratory drive. I find that very exciting, and we currently have protocols going through ethics to look at both phases of that, both in the ICU and also post-operatively. So that's the end of my talk. I don't have definitive answers if we're ready or not. There are commercial systems. The Draeger Smart Care has now moved over into the operating room, so they are clearly ready to move forward. My own take is I'd like to see us bring more of the physiological understanding that has existed since the 1960s and 70s in well mathematically formulated into our bedside care using mathematical calculations that we simply can't do in our head. Thanks very much.